Hi. So today we're going to have a bit more discussion on the array of conductors or a system of conductors. And the example I want to consider now is this pretty idealized case of a one dimensional array of conductors. So each dot here represents a conductor. And let's assume that all the conductors are identical and therefore they have the same self-capacitance, which I write as C0. And furthermore, there will be a mutual capacitance between a pair of conductors. And again, to simplify the problem, I will consider the case where the mutual capacitance is only finite among the nearest neighboring pair of conductors, like this pair or this pair, but there will be no mutual conductance between two second neighboring conductors, like, for example, this one and this one over here. And mutual conductance between neighboring conductors is negative, as we mentioned earlier. And for all the other cases, I should say a capacitance. The capacitance should be zero according to our assumption. And okay, so now we're going to assume the situation where only this one at the far left has the charge Q, and all the other capacitors or conductors have the net charge equal to zero. So in this way, we have specified the charges on every conductor. And now the question is, what is then the potential for each one of these conductors, and whether it's possible to calculate these potentials without providing any further information, but solely based on the information I have already given, which is the charges sitting on each conductor. Okay, so we can try to go back to this fundamental equation relating the charge on each conductor to the potential on every conductor in the whole system, phi, and then try to see whether we can solve this solve this a coupled problem. So for the first conductor, where as assumed we have the charge Q sitting on this first conductor, this relation would say that it's given by the self-capacitance C0 multiplied by the potential at this conductor, at this conductor at the far left, minus the mutual capacitance C times the potential on the conductor to its immediate right. And for the conductor at the far right, because there's only one neighbor to its left, the equation will be like this. However, since by assumption there's no charge sitting on this conductor, the left-hand side would have to be zero. And for all the other conductors sitting in the middle, so now this index m will range between 1 and n minus 1. So here what I'm assuming is that this conductor is labeled as 0, and this one is labeled as 1, and this one is labeled 2, and the one at the very end on the right is labeled n. So altogether we have n plus 1 number of conductors all arranged in a one-dimensional array. And these are the equations that we will have to solve to obtain the potential for each one of these conductors. Actually, this system of equations can be cast as a matrix equation. So we have this column vector corresponding to the charge on all the conductors, and we have another column vector corresponding to the potential on all the conductors. And this matrix is basically the capacitance matrix. Okay, so since the answer we want to get is for these potentials, actually all we have to do is to find the inverse matrix of this capacitance matrix, multiply that inverse matrix over here, and just perform the matrix multiplication, which will then give us the values of all these potentials. Now, the only problem with that approach is that usually finding the inverse of a matrix is not very easy, and this is some kind of n plus one dimensional matrix, which is presumably not very easy to invert. And it would be nice to have some approximate way to solve this problem without going through the process of inverting. Of having to invert this matrix exactly. Okay, so the approach is to solve these equations one by one, starting from the one at the far right. So solving this equation is pretty simple, and it will give us the potential at the far right conductor phi n in terms of the potential on the conductor to its left. Okay, and then you can further use this solution to simplify the next equation coming from this one over here to, first of all, that equation, if I write it out explicitly, will be like this. But since we know how to express phi n in terms of phi n minus 1 through this equation, we can perhaps write it in this way instead of phi n. Obviously, that's not very helpful because we still have two unknowns, phi n minus 1 and phi n minus 2. However, if we introduce an additional assumption, namely that the size of the mutual capacitance, sorry, it's very hard to find okay, here we go. The size of the mutual capacitance C is much smaller than the size of the self-capacitance C0. If we hold that assumption to be valid, and there's no reason why this is such an absurd assumption, because interaction between a pair of different conductors should obviously be less than the interaction within a single conductor itself. It's just a question of how much smaller this effect is. And we assume, for the sake of analytical tractability, that this ratio of mutual capacitance to the self-capacitance is very, very small. Well, what that assumption will provide us with is that we can ignore this first term, and then the relation becomes really simple. It's really just phi n minus 1 in terms of phi n minus 2. Notice that this is exactly the same structure as this equation we got from solving the first equation. And it's pretty clear that this structure of the relationship will continue to hold for all the other pair of conductors, as long as we uphold this approximation to be valid. Now, this recursive relation can be used over and over again until we arrive at this final form. So now you can see that the potential at the position M is just some power of this small ratio. Okay, and the only unknown parameter is the potential at the very first quantum at the very first conductor. But this one, by definition of self-capacitance, can be thought of as given by this relation, namely that the charge on this conductor is equal to the self-capacitance multiplied by the potential at that conductor. And there is a small correction term coming from the mutual capacitance to the next conductor, but since we assume that C is going to be much smaller than C0, we can probably just drop that and regard this equation to be sufficiently valid. And with this information, we can finally provide a full solution to the question of what is the potential for each conductor in the one-dimensional array, and it's given by this nice geometric expression. Okay, so what it says is that the potential being held at some finite value for the conductor at the very end over here, that potential value becomes successively smaller and smaller in an exponential fashion until it dies out pretty much to zero toward the end. Okay, so that's another nice application of this equation relating the charges to the potentials when you have a system of conductors. Okay, now let's switch the gear a little bit and think about the energy for such a system of conductors. Now, if we have a system of n different conductors, and the beauty of having the conductors as the component is that the charges only reside on the surface of each conductor. And the entire surface of the conductor is at an equipotential, phi I. Okay. So therefore, although this would be the most general expression for the electrostatic potential energy, um, in fact, for a system of conductors, this expression reduces to a discrete sum where for each conductor we have the product of the charge sitting on that conductor multiplied by the potential at which that conductor is being held. Okay, and if we further apply the equation relating the charge to the potential, then we have this expression, which is some nice quadratic function in terms of the various potentials. And there's a capacitance matrix sitting in the middle. Okay, so this is a formally exact answer to the question, what is the total electrostatic energy for a system of conductors, each held at some constant potential phi I? Of course, this is perfectly fine as a formal answer, but sometimes it's necessary to know how to express the total electrostatic energy, not in terms of the potentials, but in terms of the charges. Um, of course, if you know everything about the potential, then in principle you know everything about the charge because of this relation. And the inverse is also true, that if you know everything about the charge, then you also can know everything about the potential. And to do that, what you need is to work out the inverse matrix of the capacitance matrix. And if you have such a matrix at hand, then in fact you can invert this relation and express each potential as a function of the charges over the conductors. And what gets multiplied here is the inverse matrix of the capacitance matrix, which I write as the P. Okay, well, and using this nice expression for the total electrostatic energy becomes an equally nice expression now written out in terms of the charges rather than potentials. So if you're not entirely sure what this is good for, or whether this is good for anything, um, you can think of this probably the simplest example of a multi-conductor system consisting of only two conductors with self-capacitances C11 and C22 and some mutual capacitance C12. Well, in that case, working out the inverse matrix of the capacitance matrix is pretty easy. So this is your capacitance matrix, and therefore the inverse matrix is this guy over here, of course divided by the determinant. And just let me remind you that C12 is negative. Although I've written it as if it's a positive thing, it's really a negative number. So now once you have these information available, then you can just write this expression explicitly like this. Okay, so that's just a formal result which is valid for general, excuse me, for general charge Q1 and Q2. However, it's also useful to consider a slightly specialized case where one conductor is charged with Q and the other conductor is charged with minus Q. This should have been minus Q2, not minus Q. So we have a pair of conductors, each with equal and opposite amount of charges. Well, in that case, this expression becomes simpler because you can take out the Q square factor out in front. And then the whole expression becomes like this. So there are lots of numbers here, C11, C22, and C12. However, it's possible to define an effective capacitance like this, and then the whole expression reduces to something much simpler, like Q squared over twice the effective capacitance. So this is a little bit like working out the effective resistance in a complicated circuit consisting of many resistors, except that here we're talking about a multi-capacitor system rather than a multi-resistor system. Okay, since now we have obtained this pretty nice looking expression, I would rather spend some time talking about an interesting application of this formula. And that's something called the Coulomb blockade. Okay, so in order to explain the Coulomb blockade, I first must explain what a quantum dot is. So quantum dot is basically nothing but a small conductor. The only unique feature about a quantum dot, at least from the electrostatic perspective, is that it's extremely small. So the size of the quantum dot is typically tens of nanometers. Hence, the electrons inside that quantum dot is often described by quantum mechanics rather than classical electrostatics. Now, because of the advances in technology, it's possible to connect this quantum dot to a macroscopic system, a macroscopic conductor, and connect the two object, one macroscopic conductor and the other one microscopic conductor with some battery, and the role of the battery is create a potential difference between them. So assuming that this huge conductor is held at zero potential, um, this quantum dot conductor can be held at some potential minus phi, which is negative, and therefore, some charges can flow from this huge conductor to a tiny quantum dot. And this huge macroscopic size conductor is also called a reservoir because this is like a huge reservoir with an infinite supply of charges. And by connecting a small quantum dot to a reservoir, the quantum dot is able to borrow money, not money, but charge from time to time from this infinite supply of charges or infinitely rich bank over here. So, under this setup, the total energy of the quantum dot is this energy, which we have already discussed, plus the extra bit here coming from the fact that this quantum dot as a whole is placed under some potential phi. Okay, so that's what creates this extra term here. And now, so the structure of this expression is such that we have one piece which is quadratic in the charge, and a second piece which is linear in the charge. And anyone familiar with the structure of these parabolic curves should recognize that the minimum of this function will occur not when q is 0, but when q is some finite number proportional to phi. That's really just the high school algebra. Now, if that were the whole story, then it wouldn't be that interesting. Anyhow, but what does make this story interesting is the fact that because the quantum dot is so small, it's literally possible to count how many electrons went into the quantum dot. Like, you don't really just talk about the total charge on a quantum dot as an average of anything, but really talk about the total charge as 1 electron, 2 electron, 3 electron. So you can discretely count the total charge that are inside the quantum dot. So to emphasize the discrete nature, you can write the charge as some integer n times the charge of an electron, and that makes the this energy expression look like that. So we have the first term proportional to n squared and the second term proportional to n. And again, you can ask what value of n will minimize the total energy, because nature usually wants to minimize the energy, wants to be in a configuration that minimizes the energy. So by choosing n in the most appropriate manner, you can minimize this potential energy. Normally, you would say as you increase this potential phi, n, which minimizes the energy, also increases in exact proportion to the potential phi. In other words, n will be smoothly increased as phi increases. But remember that n now is an integer and can only be an integer because we have said that the quantum dot is so small that you can literally count just exactly how many electrons went inside the quantum dot. So n does not change continuously, but it can only change in the fashion of going from 0 to 1, 1 to 2, and 2 to 3, and 3 to 4. So the way that n increases as a function of these potential will be like a step. So it will be staying at zero for a little while and then suddenly jump to one, stays there for a little while, then suddenly jump to two, then jump to three, and so on. So that's the expected behavior. And that's in contrast to a straight line, which would be expected if n was regarded as a continuous variable. But now the interesting question is just exactly at what value of this potential phi will this jump take place? And to figure out what exactly is this threshold value for the jump to take place, we can do the following calculation. We compare the energy when the quantum dot is occupied by n plus 1 electron with the energy when the quantum dot is occupied with only n electron. And if this energy difference becomes negative, what that means is that it's energetically more favorable to put n plus 1 electron in the quantum dot rather than having only one electron in the quantum dot. So that's presumably when the jump must take place. So if you compute this difference, that's a simple piece of calculation, then you find this expression, or after a slight amount of rearrangement, you find this expression. Again, let me remind you that n can only be an integer, so n is either 0 or 1 or 2 or 3, and that literally gives us the answer we're looking for. So what this inequality is telling us is that when phi, the potential, is equal to that's when n is 0, and that's when u1 minus u0 becomes negative, and that's when the transition from a quantum dot with 0 electron occupied gives way to a quantum dot with 1 electron occupied. Similarly, the quantum dot would rather have 2 electrons than 1 electron when the potential exceeds this threshold value, and the transition from 2 electron occupied to 3 electrons occupied will take place at this threshold value of the potential. So this is a pretty simple argument which turns out to hold very, very well in the actual quantum dot experiment. So if you have a chance to read professional papers on quantum dot physics, you will find so many papers and so many data showing this sort of jump and interpretation of jumps in terms of this simple physics I have just talked about. Thank you.